Hello and welcome back to Part 10 of the Delaware Tech Physics 111 Exam 1 Preparation and Practice Exam covering motion, also called kinematics. In this section, we're going to cover vertical kinematics problems. That is, problems where an object is moving either up or down and the acceleration is constant. That's the only way we can use kinematics equations when the acceleration is constant. And if we look at the problem, it says a ball is dropped from 6 meters above the ground. Now you'll notice there's only one number in this problem. So that means we need to find other numbers that are implicit in the wording of the problem. So we have a height of how far the ball is going to be dropped. That is our vertical displacement, and we can actually start writing in numbers here. We're doing vertical displacement in our table, and we have other parameters that we usually use: the final velocity, the initial velocity. I've put them in the initial first, then final. Acceleration, but acceleration is the acceleration due to gravity, so we use g instead of a. You could still write a as long as you remember what the value for the acceleration due to gravity is. So we have a height of 6.0 meters, and we have a g of negative 9.8 meters per second squared. But if we read the question, it says the ball is dropped. That means it's just released, which means the initial velocity, the moment the ball is dropped, the very instant the ball is dropped, it doesn't have a velocity yet. So the initial velocity is 0 meters per second. Now, this ball is moving down, so what you have to realize is that while the ball is 6.0 meters above the ground, it is dropping down. So as it's falling, its displacement is a negative value. It's very important to remember that's negative 6.0 meters. All right. So what's our diagram look like? Well, we can make some height that we're dropping it from. Doesn't have to be pretty. We've got a ball at the top, and the ball's going down to the bottom, and it's going a total distance of 6.0 meters, which means our displacement is negative 6.0 meters. We also know that gravity points down, so it has a value of minus 9.8 meters per second squared. And we know our initial velocity is 0 meters per second. And you can do your diagram first, or you can do your table first. Both of them come directly from the wording of the problem itself, so it doesn't really matter which one you do first. Just make sure each of them has at least 3 initial values, 3 given values. All right, so we have our 3 given values. What are we asked for? We're asked for a final velocity, literally right before it hits the ground. Obviously, once it hits the ground, it'll come to a stop, but we're not being asked for the 0 velocity when it hits. We're asked for the velocity right before it hits. In other words, is the fastest this ball gets to move just before contacting the ground. So we're looking for a final velocity, which means we are interested in these 4 parameters, and we have to look for a formula that has just those 4 parameters in it. We don't have any information about time, and we're not being asked for time, at least not yet. So let's scroll up to our formulas to see which formula we're going to use. Remember, we need the first 4 variables. We don't need time. So if we scroll to our list of formulas, and we're looking at the vertical kinematics formulas, you'll notice that there's only one that is missing time, and that is equation number 3. Vf squared equals Vi squared plus 2g times the vertical displacement. So scrolling back, I'm going to write that formula first. Always write your formula first. and that way you know what you're plugging in where. So we have VF squared equals VI squared plus 2 times G, in this case, G, times our vertical displacement. And now we can stick numbers in. We are solving for this value, and we know all the other values. So we have VF squared, and don't forget that this term is squared. Try to get that in place here. Squared equals the initial velocity squared. Well, that's 0 squared. Well, that simplifies our equation quite a bit. Plus 2 times negative 9.8 meters per second squared times negative 6.0 meters. Now, this term will just drop out, and we're left with this term, and you'll notice we have a negative value times a negative value, which is good because we'll end up with a positive value for our product of those three numbers. Now, why is it important to have a positive value? Well, because the VF is squared, and to get rid of it, we have to take a square root. Technically, the inverse function of a square is not just square root. It's plus or minus the square root. In other words, the answer from the square root will be a positive number, but the final answer for the for the final velocity could be either a positive value or a negative value, because either one, when squared, will give you a positive number. So I'll write that out so we understand what we're talking about here. If we multiply these three numbers together, we get positive 117.6 meters squared per second squared. That unit is from multiplying meters per second squared times meters. And now we have that is equal to the final velocity squared. Well, how do you get rid of the final velocity squared? Well, you might think, oh, I'll just take the square root of both sides. Well, that's fine, but you have to remember the original number for the final velocity, whether it was a positive number or a negative number, once you square it, it's always positive. So undoing that with a square root will only give you a positive answer. So you have to basically include a positive or negative sign outside of your square root when you take it. In other words, if you have a number, let's say b squared equals x, if you want to solve for b, you don't just take the square root. You have to take plus or minus the square root of x to get what b is equal to. So b is equal to positive or negative version of x. And when you get your final answer, you'll have two answers, a positive version and a negative version, and then you have to look at your problem to decide which one is the real answer. Are they both real answers, or is only one of them an answer that makes sense? So we have this problem, we plug it into the calculator to get the square root, and it says that our final velocity is equal to 10.84 meters per second. And you might say, okay, that sounds fine, but you have to remember that could be either the positive version of that or the negative version of that, which means that when you make your final decision, you have to think, okay, what actually happened in this problem? Let's get rid of that. What actually happened in this problem? The ball was moving down. Its final velocity was downward, which means it's only the negative version of that velocity that we actually want for our answer. This is the only answer that makes sense. And this is the problem with undoing a square in a term. You can use these formulas as long as you remember that when you undo the square with a square root, it can be either the positive answer or the negative answer, depending on the problem. We only had one choice to solve this problem, so we had to use this formula. There was no choice. But when you look at the next variable, you're being asked, how long does it take for the ball to hit the ground? That's a matter of time. So we're looking for a formula that gives us time. And we can use any formula except number 3. You might want to use formula 1, which is delta y equals 1/2 the sum of the two velocities times delta t. That's the delta t we're looking for. You might want to use formula number 2, which is the final velocity equals the initial velocity plus gravity times delta t. And many students will pick 1, some students will pick 2. You could even use formula 4. But let's take a look. What would happen if you used formula 1? You plug this in, 1/2 vi plus vt, vf times delta t. You plug in your numbers. You know that this is 6.0 meters, negative 6.0 meters equals 1/2 times our initial velocity, which is 0, plus our final velocity, which is a negative number, negative 10.84 meters per second, times our unknown time. Well, the 0 will disappear, and now we have the equation negative 6 meters equals 1/2 times negative 10.84 meters per second times delta t. The negative signs cancel. Take half of this, you get 5.42 meters per second. You can do that with a calculator. Times delta t equals 6.0 meters. Remember, we've lost the negative signs. We divide both sides by 5.42 meters per second. That gets rid of the 5.42 meters per second on the right. And this gives us a change in time equal to 1.106 seconds, or approximately 1.11 seconds. And that is our change in time. That is how long it takes the ball to hit the ground. Now we can also do this problem with equation number 2. So if I scroll down, give us a little room here, and we'll write equation number 2, which is VF equals VI plus G times delta T. Delta T is, of course, our unknown, and we know that our final velocity is negative 10.84 meters per second. Our initial velocity is 0, and then we have gravity at negative 9.8 meters per second times our change in time. This term obviously disappears, and now we just need to divide both sides by negative 9.81 meters per second squared, negative 9.81 meters per second squared. This will cancel, and we're just left with this for delta t. And we plug this in, and we get the same 1.11 seconds answer that we saw when we used equation 1. So it doesn't matter which equation you use, you just can't use the equation you used for the first part of this problem. Okay, let's take a look at the next problem. Next problem is a tennis ball is thrown straight up with an initial velocity of 22.5 meters per second. That's positive 22.5 meters per second because it's going up. And it's caught at the same height as when it was thrown. Okay, why does it say it's caught at the same height? Because the ball will go up can imagine the ball going up, it reaches some maximum, and then the ball comes back down. And when you're doing these kinds of problems, it's very difficult to solve the whole problem. It's easier to solve half the problem, and you can decide which half you want, the half where the ball is going up or the half where the ball is going down. I recommend that you use the half where the ball is going up. But when they say it's caught at the same height, that's telling you that these two levels are the same and that going up looks exactly like going down. It's just it reversed in what the ball is doing. So let's just consider the ball going up. That's the easiest way to do it, I think. So you have a ball with an initial velocity of plus 22.5 meters per second, and the ball goes up, and eventually it hits a height where it's going to stop moving and then come back down. Well, if it's stopping moving in the vertical direction, then we know that the final velocity, at least final at being at the top, is 0 meters per second. So now we have a second number, even though there's only one number in this problem. And then, of course, we also know that gravity is present, and g is minus 9.8 meters per second squared. So now we have our diagram, we have all three numbers, and now we put it into our table. It's a vertical displacement property, so it's delta y. We have our initial velocity, our final velocity, our acceleration, which is g, and our time, or change in time. We plug these values in. We got minus 9.8 meters per second squared for g. We've got a final velocity for the half, for this half of the reaction, of the action. And so the final velocity is 0, and we're told that the initial velocity is plus 22.5 meters per second. So we've got our three numbers. We can now solve for anything else. So let's scroll down so we have a little room here, and it's asking how high does the ball go at the release point. In other words, the height at our final time. Well, that would be our displacement. We're solving for delta y. We're solving for how far it goes up. Well, that means we're interested in these four variables. The only variable we're not interested in is delta t. And the only formula that does not have delta t in it is formula number 3. Number 3 is VF squared equals VI squared plus 2 times G times the displacement. The displacement is vertical. So now we plug our numbers in. Our final velocity is 0. Well, that's easy to square. Our initial velocity is plus 22.5 meters per second. Don't forget to square that. Plus 2 times g, which is minus 9.8 meters per second squared, times our delta y. Well, you might want to do a little calculations before you go any further. That. And we're going to square this term first. That'll make things a little easier when we go to the next step. So if we square that term, we'll get 506.25 meters per second is also squared. So we square the meters, we square the seconds. And we can always multiply this out now, and that's minus 19.6 meters per second squared. The 2 doesn't have a unit, so it's the same units as the acceleration. And then this, of course, is still multiplied by delta y. And then this is all equal to 0. Well, if we're going to solve for delta y, we want to move terms away. And we start with the terms farthest from the delta y. Well, that would be this term. So we subtract out this from both sides, 506.25 meters squared per second squared. And we subtract that from both sides, 506.25 meters squared per second squared. These cancel, and we're left with negative 506.25 meters squared per second squared. We're not going to really worry about the units because we know we're going to be determining how high it is. So our answer is going to be in plus or minus meters. And then this is times minus 19.6 meters per second squared times delta y. Well, now it's really just a matter of getting rid of the minus 19.6, what's being multiplied by delta y, so we divide it away, basically, and we have to divide it on both sides, so minus 19.6 here, meters per second squared. This cancels, and when we divide these two terms out, we get that our delta y is equal to a positive value, because it's a negative divided by a negative, they cancel each other out, positive 25.8 meters. And that is our vertical displacement. It's positive because the ball is going up. Now, if we look at the next part of the problem, it says, how long is it in the air for? Well, remember, you've split the problem in half. You have the ball going up and then the ball coming down. So let's just figure out the time for it going up, and then when we're done, we can just double it to get our total time in the air. So our time going up is our delta t, and we can use any formula that is except for the one we just used. We used formula number 3. We can use any formula. So let's use formula number 2. That's a pretty easy formula to use. That's final velocity equals initial velocity plus g times delta t. We know our final velocity is 0. We know our initial velocity is positive 22.5 meters per second. And then we're adding that to a second term, minus 9.8 meters per second squared is our g. And that's times delta t, our unknown. We move the term that is farther away from the delta t term. That is this term here. We subtract it out, minus 22.5 meters per second. But you have to do that on both sides, 22.5 meters per second. This cancels, and this becomes simply minus 22.5 meters per second equals minus 9.8 meters per second squared. So we have a negative term and a negative term, but this negative term is multiplied by delta t. So to get delta t, we just divide this term by 9.8. We divide that by negative 9.8 meters per second squared, meters per second squared. This term disappears, and now I'll just redraw the delta t. Delta t becomes this divided by this, and when we divide that out, we should get a positive number because we have a negative divided by a negative, and our answer is 2.30 seconds. And you don't need to say positive because time is a scalar. If you want to say positive, that's fine. You won't lose any points. But remember, the problem says how long is it in the air for, so we have to just double it So 2 times that means our total time in the air, is twice that, which is, instead of 2.3, is 4.60 seconds. And this is our final answer. And we'll stop here.